Well, hi there, boys and girls. Today we're going to talk about manipulating Maclaurin polynomials, the ones that we already know, into some more advanced ones. So we're just going to get started right after this. This is our four horsemen of our Maclaurin polynomials. These are the ones that you must know. You have to know these. This is 1 over 1 minus x is the only one that has a stipulation that you can only use it for values between negative 1 and 1. That should make sense to you because this is a geometric series. And a geometric series will only converge if the ratio is in between negative 1 and 1. And on top of that, you know what it converges to. The sum is equal to the first term divided by 1 minus the common ratio. But that's only true if it's in between negative 1 and 1. Now the other three that we built, these were good for negative infinity all the way to positive infinity. So you have this written down, or maybe you do, I don't know, but you better have it written down. You have to know these expansions. So let's get after a question here. This says, let f be the function given by f of x equals an e to the negative x squared. Write the first four non-zero terms and the general term of the Taylor series for f about x equals 0. Now, since this is about x equals 0, we could have used the verbiage Maclaurin series or Maclaurin polynomial. Now, as some of you hopefully realize today, that these derivatives can get messy. It would be a bad idea to find the first three derivatives of f and then use them to build the series. You're going to get product rule, you're going to get chain rule, and you're going to get bogged down. And some of you experience that boggy downiness today. What you want to do here is you want to take your series for e to the x, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot 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 all the way out to x to the n over n factorial. This is called the general term. And what we're going to do is we're going to plug negative x squared in for all of those x's. So e to the negative x squared would equal 1 plus negative x squared plus negative x squared squared over 2 factorial plus negative x squared cubed over 3 factorial. Now let's see what happens when we replace this x in the general term. Well, that's going to be negative x squared to the n over n factorial. Now this can be written as negative 1 to the n times x to the 2n over n factorial. Because that's negative 1 to the n, and we know when we take a power to a power, we multiply. There is your general term. And the first four non-zero terms would be 1 plus negative x squared, so I'm just going to write that as minus x squared. And this next term, when we square a negative, that becomes a positive, so plus x to the 4th over 2 factorial, and then minus x to the 6th over 3 factorial. There's 1, 2, 3, 4 non-zero terms, and there's the general term. Now you need to see some other ways that negative x squared to the n can be written. So here's some other popular simplifications of that. Sometimes they won't pull out the negative 1 to the n and they'll leave it like that. And so you might see it written like any of these. So there you go for that. And let's do a second part of this. What about the function given by e to the negative x squared? Write the first four non-zero terms of the Taylor series for the integral from 0 to x of e to the negative t squared dt about x equals 0. Then use those first two terms to estimate this integral. This is the power of Maclaurin polynomials. Nobody in the world can integrate e to the negative t squared with an elementary function. Nobody can. So if we can't integrate it, we can't find an antiderivative. That means we can't find area under that curve. But watch what happens when we replace this with the Taylor series. So I have that e to the negative x squared was 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial plus dot 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 negative 1 to the n x to the 2n over n factorial. What happens if I integrate this? Well, I don't know how to integrate that, but I sure do know how to integrate a polynomial. I can integrate polynomials because it's just powers of x. How do you integrate that? Well, you add 1 to the exponent and you divide by that. So I am going to get this. Now, this is sort of backwards in that we're writing our numbers first and then increasing powers of x. So typically when we integrate, we put a plus c at the end. But since I've got it like this, I'm going to put my plus c at the beginning. So this is going to be c plus. Now, what's the integral of 1 with respect to x? Well, better put that with respect to x here. Well, that's just x. And then what's the integral of x squared? Well, that's minus x cubed over 3, because you add 1 to the exponent and you divide by that. And then what's the next one? Well, that's going to be plus x to the 5th over 5 times 2 factorial, which would be 10. Add 1 to the 4, you get 5. Divide by 5. 5 times 2 factorial is 10. So there is the first 1, 2, 3, 4. The first 4 non-zero terms of the Taylor series. Now, if you wanted to, I guess you could go out here and write the general term. It would be x to the 2n plus 1 divided by 2n plus 1 times n factorial with the negative 1 to the n. What did I do? Well, I added 1 to the exponent and divided by that. But this did not ask for the general term. Now it asks me to use the first 2 terms of your answer to estimate the integral from 0 to 1/2 of e to the negative t squared. Now, when you integrate with a definite integral, you don't need the plus c, because you plug the 1/2 in and then you plug the 0 in, and when you subtract them, the c's cancel. So I'm going to do the integral from 0 to 1/2 of these first 2 terms with x's in it. So the integral from 0 to 1/2 of e to the negative t squared dt is going to be approximately equal to using the first 2 terms here. So that's going to be x minus x cubed over 3. Now what we want to do is we want to plug in the 1/2 and then we plug in the 0, right? That's how we do the fundamental theorem of calculus. So if we plug in the 1/2, I get 1/2 minus 1/2 cubed is 1/8. So that would be like 1/3 times 1/8. So that's using the first 2 terms. And then minus, plug in the 0. Of course, when we plug in the 0, we get, well, 0. So that doesn't really matter. So this becomes 1/2 minus 1/24, which is 12/24. That's 11/24. I think that the area under the curve for e to the negative x squared from 0 to 1/2 is approximately equal to 11/24. But as I said in class, no approximation is valid or good or useful unless it comes with an error statement. So how could we use an error statement here? Explain why the estimate found in part C differs from the actual value by less than 1 over 200. How can I use an error statement? What kind of series is this? This is an alternating series whose terms are getting smaller. We can prove that here very simply. You see the terms are getting smaller. So an alternating series error says that the error is less than the absolute value of the next term. Now, I used the first 2 terms, so what was the next term I left off? You can go back and look, but the next term was x to the 5th over 10. That was the 3rd term in my expansion. So we plug in 1/2 for x, you get 1/2 to the 5th over 10, which is 1 over 32 over 10, which is 1 over 320. My error is less than 1 over 320 because this is an alternating series. My alternating series test. 1 over 320 is clearly smaller than 1 over 200, so I have just proved that. All right, so let's find a power series expansion for x squared over 1 minus x squared. Well, this one looks like our geometric series. We know 1 over 1 minus x is 1 plus x squared plus x cubed plus dot dot dot. So what would 1 over 1 minus x squared be? Well, that would be fairly simple. Replace all of these x's with x squareds. That would be 1 plus x squared plus x squared squared, which would be x to the 4th, plus x to the 6th, plus dot dot dot. Let's even look at this, what my general term here is x to the n. This general term would be what? X to the 2n, because you plug in x squared for x and multiply those exponents. Now what about this? X squared over 1 minus x squared is the same thing as x squared over 1 times 1 over 1 minus x squared. So that means that I could just distribute an x squared through here. So x squared over 1 minus x squared must equal x squared plus x to the 4th plus x to the 6th plus x to the 8th plus dot dot dot. Now if you do x squared times x to the 2n, you get x to the 2n plus 2. So there's your general term. There's your power series expansion and your general term. All right, let's do another one. What about this function, the first three non-zero terms and the general term for this function g? And it's based on e. So let's write out what e to the x is. E to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot 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 x to the n over n factorial. So e to the x over 2 would be, replace all these x's with x over 2. So that's 1 plus x over 2 plus, I'm going to put this in parentheses for now, x over 2 squared over 2 factorial plus x over 2 cubed over 3 factorial plus dot dot dot, and then x over 2 to the n over n factorial. See, I'm sort of going like a little step at a time here. So I now have this built. Now, so how am I going to build e to the x over 2 minus 1? Well, if we subtract 1 for both sides, I get that e to the x over 2 minus 1 would be all of this without the 1. So that would be x over 2 plus, now I'm going to simplify this. That's x squared over 4, and then bring the 4 down. This becomes x squared over 8. And then we have to do x cubed over 8 over 6 would be over 48 plus dot dot dot, and then it's still just x over 2 to the n over n factorial. We probably would just start at one more increment on the summation. Now the last thing I'm going to do is I'm going to divide all of this by x. Dividing by x, just term by term, we'll divide an x out of everything. So this is going to be 1/2 plus x over 8 plus x squared over 48. It asks for the first three non-zero terms. There you go. Dividing by x and just removing one power of x. And we come all the way out here. And I'm going to rewrite that general term as x to the n over 2 to the n times n factorial. It's x to the n over 2 to the n, and I just dropped the 2 to the n down. So removing one power of x would be x to the n minus 1 over 2 to the n times n factorial. So that would be the first three non-zero terms and the general term for that one. Okay, what about a series for 1 over 1 plus x squared? And what x is this valid? Use that series to get a series for arctan. You need to remember that the integral of 1 over 1 plus x squared dx is equal to arctan. So we can use known series to develop another one. So let's take a look at this. I've got this written out. 1 over 1 plus x squared from our 1 over 1 minus x looks like this. Arctan would be the integral of all of this. If you integrate 1, you get x. Integrate x squared, x cubed over 3, x to the 5th over 5, x to the 7th over 7. Add 1 to the exponent and divide by that. Now, this should be true for all values of x, and if we plug in 0 for all these x's, then we're going to get the arctan of 0, which is 0, will give us c. So we know our c is 0, and we have developed, by integrating this, a power series for arctan. Now, you do not have to memorize this, but I'm just showing you how that works. And this is valid for -1 to 1. You can't change. We might pick up an endpoint, but we'll talk about that later. But you cannot change this because the 1 over 1 minus x, that looks like a negative, so we're erasing that. This is only valid for -1 is less than x is less than 1. So if you build on that, it's still only between -1 and 1. Okay, well, that looks like I'm done, and I will see you guys tomorrow.